and Jai Hind. So I am Neha Garg, Assistant Professor in EC Department, Ajay Kumar Garg Engineering College. So today's topic is clipper, and this topic has been taken from the subject Fundamentals of Electronics Engineering. Subject code is the BEC 201. So topic is the clipper. So basically clippers are used for clipping the some part of the input signal. Like our input signal is this. So output of the clipper may be like in this form, or it may be in this form, or it may be like in this form. So so basically clipper, it will remove some part of the input signal. It may remove complete cycle, complete positive cycle may be removed by the clipper, complete negative cycle may be removed by the clipper, or some part of the input signal like this part may be removed with the help of the clipper. So clipper may basically consist of the diode, resistor and supply, and it does not have any energy storing element, like there is no capacitor, no inductor in clipper. So and it may be of series clipper, it may be of parallel clipper. If the diode is connected in series with the load, then it is called a series clipper, and if it is connected with the load in parallel, then it is called a parallel clipper. And it is also called a negative and positive clipper. If it clips the like this is if the output is like in this way, we are getting only positive cycle and there is no negative cycles in the output, so it means it is a negative clipper. The part that is removed from the input signal, that is called the negative clipper. And positive clipper is that if the if positive cycle is removed, then it is called the positive clipper. So this is a simple series clipper. In this we can see this is our diode and this is our input signal that we are giving here. So this Vm is the peak value of the input here, and also now we can see in here this diode will be so we will see in which state our diode will be in conducting state. So this is the ideal diode because no silicon or germanium is written here. This is the ideal diode. So this ideal diode will be forward biased in negative cycle of the input signal because this is N and this side is P. So N is connected with the negative side, then it will be forward biased. So for negative cycle of the input signal, so for negative cycle of input signal, the equivalent circuit will be like in this way. This would be the equivalent circuit. So here in this case diode will be short circuit and the output voltage would be equal to Vi. This is the output voltage in case of the negative cycle of the input signal, and for positive cycle of the input signal, positive cycle of the input signal, equivalent circuit would be this diode will be off or open circuit, so in that case output would be 0. So in negative cycle we are getting the output as Vi, and for negative cycle the output is equal to 0. So if we draw the output waveform, we have like this is our input and this is our input, and our output we are getting for only negative cycle we are getting the output, and for positive cycle output is 0. So for this is our positive cycle, this is our negative cycle. For this cycle we are getting the 0 output, and for this output we are getting the same as it is our input. So input our sine wave. So this sine wave would be like in this way. So this is our output. So we can see here positive cycle has been removed from the input signal. In this is our output. In output positive cycle of the input signal has been removed. So that's why it is called a positive clipper, because positive cycle has been removed. Now this is the biased series clipper. Biased series clipper means we can see here this biasing battery is connected with the diode. In previous case there was no connection of battery here, only diode was there, input supply was there, and resistance was there. So here a biasing V has been given. Now we will see in which condition this diode will be in conducting state. So we can see here we have to determine the state of the diode. So state of diode, like at P plate we can see the voltage applied at the P plate is this Vi signal and this V, and they are in opposite direction. It's this is plus minus and this is minus plus and this is plus minus. So they are of opposite polarity. So at P plate the potential is equal to Vi minus V, and N plate is connected with the output. And since we are determining the state of the diode, and in this condition diode is not conducting, so at output is 0 in this case, and hence the at N plate the output is 0. So and always the potential at the P plate is always greater than the potential at the N plate for the diode to come in the conducting state. That's why the condition for the diode for conduction is Vi minus V greater than 0. So in this condition, diode conducts. So this is the state. We have determined the state in which our diode will conduct. So simply we have to put that at P plate potential is always greater than the potential at the N plate. In that condition only diode will be in forward bias and it will be in conducting state. So this is the condition, that is Vi must be greater than V. This is the condition, and in this condition equivalent circuit would be, now our diode will be short circuit in this case. So equivalent circuit will be like this is the resistance, this is Vi plus minus, and here plus minus V, and this is V naught. So V naught would be equal to Vi minus V. We can apply KVL here, and from KVL we can see the from the KVL we can see the output V naught is equal to Vi minus V. Okay, so in now we have in this condition Vi greater than V, diode conducts, and for Vi less than V, diode does not conduct. For Vi less than V, diode does not conduct, and in that case equivalent circuit would be now the diode will be open circuit, so it will be like in this way. Okay, so in this case the output would be equal to V naught would be equal to 0, because this diode has become open now and no current will flow through this circuit, so output voltage would be 0 in this case. Now how we will draw the waveform? So for waveform, this is our input signal and output would be now this is plus V, so we will draw a line of plus V from here. This is our plus V, and from here we can plot a this way. Okay, so this is the A, this point is A, this point is B, this point is C, this is D, this is E, F, G. So different points are there. So we have to find the conducting region. So our conducting region is Vi, that is greater than V. So this level is V. So Vi greater than V is this part. So this part is our conducting region. So in conducting region our output is Vi minus V. So at point B, output is V naught is Vi minus V. So here we will put the value of Vi, that is equal to at this point Vi is equal to V. So V minus V is equal to 0. So at point P output is this 0, and at point C point output is V naught is equal to Vi minus V, and at point C the value of Vi is Vm. So it would be Vm minus V. So here output is Vm minus V. So this is Vm minus V, and again at D point output would be 0. This is 0, and again at F point. So this region is the non-conducting region, and at non-conducting region this rest of the region A, F, G, all this region is a non-conducting region, and in non-conducting region our output is 0. So here output is 0. Throughout output would be 0. So this is the output waveform of the clipper. So here we can see negative cycle. Negative cycle is completely removed from the output, and in positive cycle we are getting the peak value of Vm minus V. So this is basically a negative clipper because it has completely removed the negative cycle, and biased also because it is with the help of this spicing we have modified the peak value of the output signal. After that, biased series clipper. So this is the next configuration in which we have changed the orientation of the diode, and here we can see the input signal is our sine wave having plus minus Vm value is there. So at we have to first determine the condition in which our diode will conduct. So and at N plate we can see at N plate potential is Vi minus V. Vi minus V, because Vi and V both are against each other, though their polarities are against each other. So Vi minus V is the net potential across the N plate, and at P plate potential is 0 because there is we have currently we have determining the state of the diode. So in this state the output voltage is 0 here. So that's why at P plate potential is 0, and we know that the diode will be in forward bias when the P plate potential will be more in comparison to the N plate potential. That's why Vi minus V must be less than 0 or Vi must be less than V. For this condition diode conducts. And for this the equivalent circuit would be like in this way. So this is the equivalent circuit for the clipper. In this case diode has become short. Now the output voltage in this case would be V0 would be equal to Vi minus V. Now the condition in which our diode will not be working, so Vi greater than V, diode does not conduct. For this condition diode does not conduct. So equivalent, now this in this case the diode will become open circuit, and equivalent circuit would be in this way. So in this case the output voltage would be equal to 0 because diode is open now and there will be no current flowing in the circuit. That's why output voltage V0 would be 0. So in this condition we have obtained the output as Vi minus V, and here in this condition output is V0 is equal to 0. Now we have to draw the output waveform. So this is our input waveform. So from this we will plot the output waveform. So our threshold value is Vi less than V. So we will plot Vi, we will plot this is our, okay, I will plot here. This is our input signal is there, and this for this output is here, and we have to plot, this is our input, we have to plot the V line. So this is our V. Now from this point we will draw the perpendiculars. Now the we have to find the conducting region. So conducting region is Vi less than V. So this is our V, and the Vi less than V is the this part. So this part is conducting. So in conducting part, output is Vi minus V. So if we take this point, this is A point, this is B point, C point, D point, E point, F point, and G and H point. So at A point, if I take A point, output is Vi minus V, and here already Vi is at 0, so it would be minus V. So here output is minus V, and at point B, Vi is equal to V, so it would be 0. So here it would be 0. So we can touch this, this is 0, and after this again this is, okay. So in similarly we can obtain the output as G also. So G, at G it would be Vi minus V, at G the Vi value is minus Vm, so it would be minus Vm upon V. So here it would be minus Vm minus V. So this graph would be like in this way, it will extend. Okay, by putting the values of output voltage, that is Vi minus V, we can obtain the output at every point. So these are the different configurations for the series clipper. This is the simple series clipper where there is no biasing here, and the orientation of the diode is in such a way so that it will be forward biased in negative cycle, and for negative cycle we are getting the output. So that's why here only negative cycle is visible here and positive cycle has been removed. That's why it is a positive clipper, because positive cycle has been removed. And in this is also a simple clipper, and orientation of diode is just opposite of the orientation of diode of here. And in this case, this diode will be forward biased in the positive cycle of the input signal. This is our input signal. So for this cycle, the diode will be forward biased, and that's why for that cycle only we will having output. And for negative cycle, this diode will be reverse bias, open circuit. That's why there will be no output in the negative cycle. That's why it is called a negative clipper. And these are the cases with the biasings. We have applied biasings with the diode also. And here the orientation of the biasing is plus minus V, here minus V, just reverse. So output waveforms will be like in this way. We have taken these examples in the previous slides also. And here the orientation of the diodes are just opposite to this. And here in both diagrams we have changed the polarity of the V. So these are the all these are the negative clippers, and all these are the positive clippers. So till now we have discussed the series clippers. Now this is a parallel clipper. Now we can see this diode is in parallel with the supply or parallel with the load resistance, and in that case diode was kept within series with the resistance. So here we can see this diode will be forward biased for the positive cycle of the input signal. For positive cycle of input signal, diode is forward biased. So equivalent circuit will be like in this way. Okay, so in this case the output voltage would be equal to 0, because we can see the output is we are taking between these 2 points, and these 2 points have been shorted. If there is a potential VA is here, the same potential will be VA will be here. So the potential difference will be VA minus VA, that will be 0. That's why here the output voltage would be 0 in this case. And for negative cycle of the input signal, diode will be reverse bias. And in that case, equivalent circuit would be equal to V naught would be equal to Vi, because this diode has become open now. So all the input voltage are expressed across the V naught. So V naught would be equal to Vi. Now we will draw the output waveform. So this is our input. This is Vm plus Vm and this is minus Vm. This is our input and this is our output. So we have seen that for positive cycle output is 0 and for negative cycle input is equal to Vi, that would be equal to V minus Vm. So this will be the output for this such type of parallel clipper, because in negative cycle we are getting the output Vi, that is equal to minus Vm. So this is basically a positive clipper because positive cycle has been removed. Now this is the biased parallel clipper. Previous one was the simple parallel clipper, and because we have applied this battery here, V here, so this has become the biased. With the help of this biasing, we can change the moderate the value of the cycle that will be present in the output signal. So here now we have to find in which condition our diode will conduct. So at P plate potential is Vi, at P plate potential is Vi and N plate potential is V. And for the diode to be in conducting state, the potential at P plate must be greater than the potential at N plate. So the condition would be Vi must be greater than V. For this condition diode will conduct. And for that case equivalent circuit would be like in this way. In this way V naught would be equal to Vi, sorry, V naught would be equal to V, this is V. In this case output voltage would be equal to V, because this V is in parallel with the output. So output voltage would be equal to V. Now the condition in which our diode will not work. So that condition is Vi less than V. For this condition diode does not conduct. And in that case the equivalent circuit would be now the diode will be open, so equivalent circuit will be like in this way. So in this case output would be equal to V naught would be equal to Vi, because this circuit has been diode has become open, so no current will flow through this arm. So whole input voltage will be expressed across the output voltage and V naught will become equal to Vi. Now the waveform. So this is our input waveform. Now here we can see the threshold amount is plus V. So we will take here plus V. Now we will draw the intersecting lines. Okay, so here we have to find the conducting region. So for Vi greater than V our diode is conducting. So this region Vi greater than V is this much. This part is Vi greater than V. So this part diode conducts. For this part, diode conducts. So see, this is A, B, C, D, E, F, and G. They are the different points. So all these A, B, D, E, F, G, all these are the points where diode is not conducting and output voltage is equal to Vi. And for this reason B, C, D, this reason the output is equal to Vi. So equal to V. So we can put here it is equal to V, and for rest of the reason it is following our Vi signal. So our output will be in this way. For the conducting region BCD it is V, and for rest of the region it is following as the input signal. So this is basically a positive clipper, and that is biased because some amount of the positive cycle has been removed, not the complete positive cycle has been removed. So that's why it is a biased clipper. Now this is the another configuration for the bias parallel bias clipper. So here we have done the orientation of the diode as reverse, and polarity of the biasing has been also reversed. So in this case again the P plate of the diode is connected with your minus V, and N plate is connected with Vi, and P plate potential is always greater than the N plate potential. So minus V must be greater than Vi, or we can say Vi must be less than minus V for diode conducts. This is the condition for our diode to be in conducting state. Now the equivalent circuit would be equal to, now the diode will be in short. So this would be the equivalent circuit. So this output would be equal to minus V. Here in this case output would be equal to minus V because here minus and plus, and here plus and minus. So we can apply KVL in this part and output would be equal to minus V. And now in another condition in which diode will not conduct. So for this condition diode will not conduct. In that case the equivalent circuit would be equal to, the diode will become open now and circuit will become like in this way. So in this case output voltage would be equal to V0 would be equal to Vi, because no current is flowing in this arm and all the input voltage expressed across the output. Now the output waveform would be, first we will draw the input, this is our input, and we have a threshold line is minus V. So we will plot here minus V, this is minus V. Now intersecting lines will be there. So conducting region is Vi less than minus V. So this part is conducting. This part is conducting. So for conducting region the output is minus V. For conducting region this part is conducting, means like this is A, this is B, this is C, D, E, F and G. So D, E, F part is conducting, and in conducting part output is equal to minus V. So here it would be equal to minus V, and rest of the part it will follow as the same as the input signal, because in rest of the part output signal is equal to Vi. So here in the conducting part output is minus V, in rest of the part it will be following the input signal. So this is basically a negative clipper, and also with the biasing is there. So all these configurations are for the parallel clipper. Here we can see this is the simple parallel clipper, and this diode will be forward biased only for the positive cycle. So it will be at the output we will getting only in the negative cycles here. So this is the for the positive clipper, and here in this positive clipper we have applied biasing here with plus V polarity, and here with minus V polarity we have done, and these two these are the output waveforms, and this is our input waveform for which we are getting these outputs. And this is another simple parallel clipper that we have discussed in previous slides also, and in this case this diode will be forward biased in negative cycle, and we are getting the output in the positive cycle because this has been used in the parallel configuration. And also here V biasing is there negative, and here V positive biasing is there, so these output waveforms will be there. So this is the example for the combined clippers where we have used two diodes, and till now we have seen with the only single diodes was there, but here two diodes are there. So we can take this as a D1 diode and this as a D2 diode. So for D1 diode we can see D1 diode will conduct when Vi would be greater than V1, and for D2 it will be conducting when Vi is less than minus V2, because for D1 we can see P plate is connected with Vi and N plate is connected with V1, so Vi must be greater than V1, and here at D2 N plate is connected with Vi, P plate is connected with minus V2, so minus V2 must be greater than Vi. So these are the conditions in which our diode will be in conducting state. So we can write here, we can make a table this is the condition, and D1, state of D1, state of D2, and our output. So this will be the, now for V1 greater than Vi, Vi greater than V1, here Vi less than minus V2, and here Vi is less than here we can write as like V1 and minus V2, and Vi is greater than minus V2 and V1 is greater than minus V1. Okay, so these are the conditions. So for this condition Vi is greater than V1, we can see our diode D1 is on, and for this condition diode D2 is off, and for this diode D2 is on and this diode is off, and for this condition both diodes are off. So here it will follow Vi, and D1 is on, so it would be plus V1, and here it would be minus V2. Okay, so these are the conditions and these are the outputs that we have obtained. So for Vi greater than V1, we can see our diode D1 will be on and diode D2 will be off, because if we plot here, so our V1 would be like in this way and minus V2 would be in this way. So this is the conducting region for D1 and this is the conducting region for D2, because D2 is conducting for Vi less than minus V2 and D1 is conducting for Vi greater than V1. So this is for this shaded region is the conducting region for D1 and this shaded region is the conducting region for D2. That's why for this condition both diodes are off, because these conditions are just opposite of these conditions written here. And if both diodes will be, this diode will be off, this diode will be off, so both will be open circuit. So no currents will flow through these arms. So our total input voltage will be expressed across the output, and that's why output would be equal to V1. And if this diode will be on and this will be off, so it will be open circuit and it will be short circuit. So output voltage V0 would be equal to V1. And if in another condition when D1 is off and D2 is on, so D1 will be open circuit and D2 will be short circuit. So output voltage V0 would be equal to V2. So this is the conditions that we have obtained. Now we can plot the output. So this is our input waveform and this is our V1, this is our minus V2, and we will draw line like in this way. like, so this is the conducting region for D1, this is the conducting region for D2, and for conducting regions the output is like this, for this it is V1 and for this it is minus V2. So here in rest of the region it will follow the output signal. So this would be the output for the parallel clipper. So now this is the next question in which we have taken the silicon diode, that is our practical diode, not ideal diode. In case of the ideal diode, the barrier potential we have taken is a 0 volt, and in case of the silicon diode it will be 0.7 volt. So this diode will be conducting, so this diode will be in conducting state when Vd must be greater than 0.7. Vd and Vd would be equal to Vi. So when Vi greater than 0.7, or we can see, we can write it as here, Vi would be equal to, this is minus, this is plus, minus plus, and here this is plus, this is minus Vi. So the value of Vd would be equal to Vi plus Vd. So it would be equal to minus Vi greater than 0.7. This is the condition when this diode will be in conducting state, or we can see Vi must be less than minus 0.7. This is the condition in which diode conducts. Okay, or when this diode will conduct, output voltage would be equal to, this diode will be replaced with the 0.7. This is Vi, this is 0.7. So in that case output would be equal to Vi minus 0.7, Vi plus 0.7 minus Vi plus 0.7. Output would be equal to Vi plus 0.7. And if condition is like this, so diode will not conduct and output would be equal to 0 in that case, because diode will become open and no current will be flowing, and in that case output would be equal to 0. So output waveform would be like in this way. This is 20 volt, and this threshold line is minus 0.7. So this is 0.7. Now conducting region is Vi less than minus 0.7. So this region is the conducting region. So in conducting region we can see this is our A, B, C, D, E, F, G. So we can draw the line here. So in conducting region at D point output is Vi plus 0.7. So here the value of Vi is minus 0.7. So that's why it will be equal to 0 at this point. And at this point it will be equal to, at E point it will be equal to minus 20 plus 0.7. So it will be equal to 19.3 minus 19.3. So here it would be equal to minus 19.3 volt. Otherwise it would be equal to 0. So this is the output waveform. Okay. Now this is another question. So here also we have taken the practical diode, that is Si, and if there is no Si written here, it means it will be a ideal diode, and we will, in forward bias, we will key diode, we will short the diode, but here we will replace this diode with 0.7 volt. So here we have to find the conducting state of the diode. So for conducting state, we know that Vd must be greater than equal to 0.7. Okay, now we have to find the value of Vd. So for finding the value of Vd, we can use this technique. So we can apply KVL here. So Vi minus Vd minus 4 is equal to 0. So Vd would be equal to Vi minus 4. So we have obtained the value of Vd as Vi minus 4. We know Vd must be greater than 0.7. For only in that condition our diode will be in conducting state. Now we have to find the value of Vd. So we can find the value of Vd with the help of this circuit, and Vd will be equal to Vi minus 4. So in that equation we can put here Vi minus 4 must be greater than equal to 0.7. That is Vi greater than 4.7. So this is the condition that we have obtained. So now for this condition, diode conducts. Okay, and when it will conduct, the equivalent circuit would be equal to, this will be replaced with 0.7 and this would be equal to 4 volt. So this is 0.7 volt plus minus, this is plus minus 4 volt, and this is Vi R. So in this case, output voltage would be equal to 4.7 volt, because 0.7 and 4 are in series, so we can add these voltage. Output would be this. So if Vi is less than 4.7 volt, so in that case diode will not conduct. And in that case circuit will be open and output voltage would be equal to 0 in that case. And now we have to draw the input waveform. So this is our this, and now Vi must be greater than 4.7. So we will draw the line of 4.7 here. This is the line drawn for the 4.7. Now we will draw the intersecting lines here. So this is the lines. Now here the conducting region. This region is conducting. This region is conducting. This part is conducting. So at conducting part, output is equal to 4.7. At this part, output is equal to 4.7. And in rest of the part here the output would be equal to Vi, not 0, because this is a parallel configuration. So here it would be equal to 4.7, and rest of the part it will be following the input signal. So this is 4.7 volt, and rest of this part it will be following the input signal. Here when diode will not be conducting in state, output would be equal to Vi, because this diode will be open circuit and this whole Vi will be expressed across output, and this is a parallel configuration. In parallel configuration, when diode is not in conducting state, output is always 0. So these are the applications of the clipper. We have seen that clippers, we can use the clippers for clipping some part of the input signal, and desired part or a complete cycle may be removed from the input signal, and it is also used for the protection of the transistors from transients. And a frequently used half wave rectifier in power supply kits is a typical example of clipper. Clippers can be used as a voltage limiters and amplitude selectors. For generation of new waveform or shaping of existing waveform, clippers are used. In next lecture, we will see the clampers, how clampers are used in the electronic circuits. Thank you.